Hi, my name is Krzysztof. I'm the principal solutions architect at Neptune AI, which is the experiment tracker trusted by top research teams at companies like OpenAI, Poolside, Bioptimus, and many more research labs, big and small, that are training foundation models in a serious production way. Over the past few weeks, Leo, our product specialist, and I did a little bit of a challenge for ourselves. We put ourselves in the shoes of our users, of top researchers doing real development of foundation models. So Leo, I believe you focused on pre-training of kind of like transformer style, GPT style large language model. Well, I worked on diffusion model, and today we'll show you how that worked and how we use Neptune to power our day-to-day research tasks, how to ensure that you capture every bit of information at the scale and like production frequency and the reliability required by top labs. We'll talk a little bit about debugging, about experimentation that goes into developing these large models. We'll also talk about how to optimize resource usage as you run many evals and training jobs in parallel. The necessary kind of like messy part of the iterative research process that it takes to develop these models. So speaking of iterative process, I think that's a good point to start. So maybe you can walk us through the few bits of experimentation that you did as part of your LM development, Leo.
Yeah, so basically, as you mentioned, I focus on GPT-style transformer. I am not an AI researcher, so it was really great to put myself in these shoes, and I did a lot of research on what I should do. But essentially, I found that I could do some continued self-supervised pre-training on a GPT-2 model that I found on Hugging Face's Model Hub. And I saw that I could potentially continue training GPT-2 and see how its performance would improve on mathematical tasks. To do that, I did some ablation studies to see how the model's layers were reacting and what was important. I did some hyperparameter optimization, if you can call it that, to determine the optimal hardware to use for my continued pre-training. A little bit GPU poor. For this, we only had a couple weeks and we didn't have massive amounts of GPUs available, but did a little bit of optimization on that. And then I went into, once I had the architecture I wanted to use and I had the hardware that I wanted to do for this distributed training, I then did a couple of longer experiments, tried some upscaling of GPT-2, tried to just continue pre-training GPT-2 to see how its mathematical capabilities ran. And on that, I then had to track things like the aggregated metrics. I had to track model internals on the new layers I added to the model. I also had to track things like the evals on public benchmarks, especially ones that were math related, to see whether or not the model was learning any new knowledge for mathematical capabilities. And yourself, Krzysztof, what did you go and work on?
Yeah, so while you were doing all the intense early experimentation and then production training monitoring, I did a little bit of an easier setup with a diffusion model. So I think in my mind, maybe with little, but some data science experience that I have, the diffusion models are simpler to train than transformers. I did try to productionize the training loop a little bit to, well, maybe not entirely build a model factory like some of our customers. Like I think Poolside had a cool blog post about that. So not quite there, definitely not quite there, but like a starting nugget of what a production grade model factory could look like with a centralized platform library for monitoring, like hardware, model internals. So similar to your setup. But then because of the specifics of my model, which was a class conditioned diffusion model generating handwritten digit images, where obviously digit is a class and that's how the model knows what to generate and learns what to generate. I focused a lot more on evals, because in diffusion, as your loss kind of like starts to converge very, very slowly, almost flat lines, you still get model improvements that are very subtle but very meaningful to the final output, and you really need to track how the outputs look and how accurate they are on various subsets of the generated samples and various tasks related to those. So I am tracking a lot of eval metrics. I will show you in a moment. I know you used evals as well, so it would be fun to compare the two. And yeah, I think we'll start this maybe by showing the training loop that I wrote, because I think that's maybe like a good intro to how a high quality monitoring setup could look for that, and then we'll move on to your experiments and finish with the evals. How does that sound?
Yeah, that sounds great. I think we should just jump right into it.
Yeah, let's do it. This is a very simple set of scripts that I use to run the training, run the evals, and to do some debugging, forking, and so on during my longer training runs. This is a foundation of everything that I imagine big labs develop upon when they start the like more intensive training of those like big models. So as you can see, I have a script that can do basic trading. So all you need to do is you can run run train.py new or resume or fork, depending on whether you're starting from scratch or you're loading from a checkpoint and you want to test a different idea.
Yeah.
And the foundation of the script, regardless of the fork, resume, or new, is this basic training loop. The kind of context, whether you're starting from scratch or not, it initiates the Neptune run and loads the checkpoint slightly differently. But then the standard training loop is really doing what you would expect. So it creates a data set with a pipeline to load those well, in this case, images. It has a debug mode that allows you to track various tensor stats from each layer.
Yeah.
So you can turn that on and off, and you can customize which stats are tracked. And
Is that during training?
It could be during training, or you could fork and run a debug mode as well.
Yeah.
But I find now that actually I didn't run it with debug on at all times because it is slightly faster if you're not capturing everything.
Of course.
But I found that I wasn't capturing nearly enough when I failed a couple of my runs, and I'll show you later what that means. I think in retrospect I should have at least tracked the gradient norms for everything.
Yeah,
and maybe even maybe even some of the activations, like histograms of like the most important activation layers, just to be on a safe side, even during the production kind of like fast training. So that's actually what this utility is for the Torchwatcher. I think we open sourced it already.
Yeah, we did.
So it allows you to just plug in your PyTorch model and the run that you used in Neptune to track the stats. And I'm using this one to track all the debugging metrics. And I also have another utility called System Metrics Monitor that also takes a run. And it's in background it pulls the like hardware for metrics such as GPU utilization and like memory utilization and so on to make sure that I'm using my hardware effectively. And as you can see, this is actually a nice thing about using Neptune for this is I have my run and it's perfectly composable. So I can pass it to different functions and and log from the main process, and it all works out quite well. There's like no problems related to the like multi-processing, multi-threading that I found, and I really liked it. Awesome. But the basic training loop is like we log all the configs. I log all of them here, which makes it easy because when I change something, I sometimes have a parameter in my script. If it's like something that I change very often, like batch size, maybe when I'm moving to different GPUs. But other things I might only change in the code. And because this logs everything as a config to Neptune just before I start the training, I'm not losing any of the config attributes regardless of where I change them. So I'm logging the configs, and then I'm doing basic training step with the watcher for the metrics if we're like in the debug mode. And it's easily like basically like the most like basic training loop that you could see in an example online, right? It's a basic forward pass, backward pass, and then we're logging the metrics. So the metrics that I'm tracking here, these are the what most people think of an experiment tracker. They think of these like loss, step, epoch if you're like using multiple epochs. And then I'm saving a checkpoint. So checkpoints don't go into Neptune; they go into like a volume mounted to the training job.
Okay, so some sort of blob storage.
No, I think it's like a block storage. Yeah, it's like it's a network dismounted. So that is usually faster for just like large scale data. But I'm still logging the checkpoint paths and then saves time to Neptune just to have this like reproducibility in the end if I need to pull the data from Neptune. And so that's how it looks in the code. That's really it.
I noticed you created your own training loop in this case, right?
Yes.
So on my side, what I did is I actually used another training framework. It was particularly Hugging Face's training framework.
Okay.
And I used a callback that I logged everything through. But definitely see that you're using this custom loop. Do you see any benefits, or have you spoken to people of why they would use one approach over the other?
Yeah, it's a great question. For me, the benefit is I have full control.
Yeah.
I am not training models every day anymore. I did that in the past, but not at this caliber either.
Yeah.
So I like to have control and understand what all the utilities are doing and where exactly the data is logged from, but also how the actual training mechanism works.
Yeah.
So that's why I opted for like a linear approach with direct training loop implementation, which, as you can see in this case, it's still simple because the code, I think it's nicely organized and composed of different libraries, utilities.
Yeah.
With Neptune, obviously, as you said, right, like you have the option of going with a framework like Lightning or Hugging Face, right? And that works equally well. I think the library is well developed in my mind, like well designed. The APIs, the run and API and so on. So we can actually compose it pretty easily. I just didn't really want to learn so many additional frameworks.
Yeah, of course.
So that's, I think, down to preference.
Yeah. What I hear from clients is that, or people that we talk to that are doing these trainings, that they would maybe start with a framework like a Lightning or a Hugging Face, get training going quickly for maybe some smaller scale. So especially when they're doing like the ablation studies, or they're doing some sort of hyperparameter optimization, so to get something going. But then, like you say, as the training scales, they want to have a lot more control. They want a little bit lighter weight, very focused wrapper on what they need to log, so that it aids that kind of throughput of optimizing their GPU time and things like that. So definitely see that as well.
As they grow bigger, they basically have to customize a lot more. So the big labs, the like 100+ people labs, like 20, 30 people sometimes, they do have their own, like we talked about Model Factory, they do have their like MLOps platform. MLOps might not be the word they use for that, but it's really what it is. It's a standard library of code for checkpointing the trainings, running the experiments, logging data, allocating hardware, even like stuff like that. And I think this shows you that you can compose it, Neptune into it pretty easily.
And also think in different domains, those frameworks don't always have everything that they need. So they might be working with biological data that they need to do some sort of customization on, or time series data that they're also doing some sort of customization on. So to get going is really easy, but then they need to start customizing it to their specific domain.
Another cool one is the word models, video space. They get like so data intensive that you have to customize a lot, because you're paying a lot, not just for GPUs but also for the data throughput, the storage, and so on.
And the more lightweight you can make it, the better. The easier
to customize, I think so. Should I show you how it looks like in the web app?
Let's jump into the web app.
So here we have the web app with some of the training experiments that I logged using the script. Just showing a few last ones. So first of all, what we get is the basic metrics like loss. Obviously, you see that there's this one experiment that kind of exploded completely. So that's the one where I wished I had more data for this part, because when it exploded, I ran it with debug mode, but I didn't have a lot of data from like the middle part, and I should have just tracked more metrics, to be honest. But other converge nicely, and you can see for some of them, you can see the forking points, right, where I changed a little bit of parameters, and the loss changed as well. And you have the...
How did you see that? How did you see the loss change? How did you know that the loss was changed? Was that just in your tooltip?
Well, I see it on the chart when I hover over it, right? It's the brown line. Cannot hover on the exact loss point, but here it changes, right?
But what I mean is, how did you know that was the particular parameter that you changed? Just because you remember that, or are you seeing it in that?
I remember that. I think you can. So this is basically the last experiment, but if you go into the runs for this experiment, you can actually see all the runs. Maybe I can show you a little bit of that, how that works. Let me just copy the experiment name and filter the runs. Because I do use the tags in the experiment name, but if I go to runs, I see all the runs, and I use the prefix to kind of like see the ones that went into this one, right? So we have 2001, 2101, 2103. So this one was forked multiple times because some things exploded there. So that's why you have 03 in this one, not the one. And yeah, so I see all the different variants, and you can even see the one that exploded. I think it's one of them, right?
Yeah.
Yeah. So 200101 didn't work, but 03 I lowered the learning rate here, and this one actually had another error that I needed to fix. So yeah, so that's how it went, and then we get lower with the loss in the end with this one with LR minus 10 to minus 5. And we change the noise as well on the data. So yes, that's how you see the lineage of these runs tracked over time, and you can obviously turn the inherited metrics on and off, and then you see like only the part for a given run. Obviously, the scale changed quite a bit, and that line is no longer continuous, so that's why you get this weird blip in here. But you see how the different components of this one experiment worked, basically. Well, it's not one experiment technically, but it's the chain of experiments that I run that depended on one another, and all that forking information as well is captured. So if you go to any of these runs, sorry, I need to click on this one, right? So if you go into sys forking, you can see the depth and the parent run ID that was actually captured. So I actually use this in a programmatic way in an API where when I run evals, which is the other script that I need to show you later. When I run evals, I gather the entire forking history of the experiment, because when I load checkpoints, sometimes the checkpoint is from the parent run. So I need to know how it was just the path convention that I used, but it's a very commonly used one, right? You need to like find your like lineage of experiments programmatically, and then depending on like which step you load, it might be the parent of the parent of the parent that you load, and so on. So yeah, all of that can be done. And yeah, maybe while we're here in the attribute stuff, the sys ones are the ones tracked by Neptune automatically. They're all documented, so I'm not going to maybe go into them too much, because I think we have excellent docs. But for the training, as you can see, I'm capturing the basic metrics like loss, and then like also like tracking step and the global step, and I'm also like tracking some performance metrics, even like the step time, to just make sure that like as I'm maybe like launching a new GPU instance, is the GPU they're actually like on par with what I'm expecting, or did it get like slower or something like that. I have my debug metrics. So as I said, like I'm not tracking all of those, but for some of those runs, I have some debug metrics as well. So we have the class embeddings here. We have all the layers basically, and we're capturing the activation metrics and gradient metrics. And gradient norms are really like the most useful ones.
I see there's like these shadows that appear on the graphs. What is happening there?
Yeah, so it's basically because of the data scale. Neptune does not really average any data or downsample it. So what you get for each kind of like pixel on the chart or bucket on the chart is you get the average value shown as the main chart. But if you zoom in, you can see that actually it's a lot more spiky, right? So that's where the shadows appear, because there's some range of those values.
Okay.
So it never hides the data from you, regardless of how many steps you have. It shows you all the actual data. So you always see a spike, right? Like for instance, the one here is actually much higher than the colorful one, but you still see the shadow of the spike that is like all the way to 0.1, right? And when you zoom in, you can see that there's like one data point that's so high, everything else is actually kind of normal. So yeah, that's why there are so spikes, especially in this like noisy charts. If you look at like something like loss, it's usually, hopefully it is a little bit smoother. This one is not actually, but the range is also not so bad. But yeah, so I have my training metrics here. I also have my eval metrics, which we're gonna go into later. I have what I mentioned about the checkpoints. I'm also tracking the save times, the paths as these are string series. So we have everything just in case. And I even went as far as capture the training environment. So we have all the source file, like train, that's the script that I literally showed you earlier, right? Mm-hmm. Captured here as a snapshot of what it was when I triggered the run. the library files as well.
So it's great for reproducibility.
Exactly. Or also great for finding things that I messed up and forgot to log.
Oh, yeah.
But it's always in the source code. Like if it's not logged, it's definitely in the source code. So I also have my Git information. This is actually captured automatically by Neptune right now. And same as like entry point. You can see that like these are the command line options that I used. So yeah, I think it's pretty cool. It definitely helps reproducibility to have all those configs there just in case. And even with that, I once had to add a little bit more, like halfway through the training. So yeah, I wasn't really like upset with myself not adding some of the logging earlier. So yeah, this is how it looks like. Maybe I can show you some charts. So nice thing about this is we can like search quickly, right? So if I want to have all my like gradient norms, I can put them up in one screen. And it's really easy to search through that when you're debugging. I'm sure you also found that as well.
If you just want to search through your debugging metrics, just use that regex and you can find exactly what you're looking for really quick.
Right.
Yeah, very, very quick. You can also look through all of the hardware metrics as well, just to kind of correlate to was there anything happening somewhere, and find those pretty quickly. I didn't have to wait for anything to load.
Should we jump into your section now?
Yeah, definitely. We can jump into the little bit of research that I did, and I'd love to show you the ablation studies. Essentially, GPT-2, as you probably know, it was trained and it definitely converged. But I did a couple of ablation studies just to understand how the different layers on this model was working, right? So when I was doing these ablation studies, I tracked a couple of different things. I wanted to see how stable this model was. So I tracked the standard training results, like the losses, calculated some perplexity on the eval losses, just to ensure that the model was converging at a high level. But I also went and tracked some of those model internals like you did. So I wanted to make sure that all of the model's layers were stable. So I tracked my gradient norms, and I tracked a whole bunch of activation layers as histograms, just to see kind of that distribution of the layers and how this model was performing. So when I was looking at what I need to answer during an ablation study, 4 main questions came up. Did any of the ablations make training unstable? Did removing a component hurt performance significantly? Did some changes improve convergence speed? And are any of these layers particularly critical? So I wrote these observations down so that I could answer these questions as the ablations were going. So what did I do for this particular study? There were a few different things I did. I took GPT-2 and I manipulated some of the layers. So the one was I ablated the dropout. The other one was I disabled the gradient clipping of the model. And the third one was I ablated the particular layer norm, just to see how this model was performing. I read on one of the blog posts that somebody else went to try to train GPT-2 that when they ablated the dropout, they actually got better performance. And I wanted to validate that for myself, because as we said earlier, we didn't have a lot of GPUs to this. So the faster the model could train, the better, leading into kind of these longer training monitoring runs. So that's what I did. I've got these 4 particular experiments that I then ran on a tiny stories data set, just to use one of them. And what I also did is I randomly initialized all of these weights. Even though in the longer training, I'm going to do continued pre-training, so to keep the knowledge embedded in the model, but to understand the stability of this model, I randomly initialized all of the weights with the same seed to see how this performed. So to answer the first question, if we go up to the training results, did any of these ablations make training unstable? What I observed that is no. Nothing that I particularly did made the loss not converge. As we can see in the training loss, I ran this for about 30 million tokens. If we zoom in, you can see that pretty much all of these did converge. So there wasn't any particular instabilities. But if we went and looked at the beginning of this training, what you will notice here is that for the version where we ablated the layer norm, you could see that in the beginning, all of the layers did have a kind of increase in their gradient norms at about the 300,000 token mark. If we go out, you can kind of see.
Just to ask a quick question. So the colors on this chart correspond to different experiments, but the different styles of
the different lines are the different layers. So if we look at our legend, you can then see that my different layers are grouping by different line styles. Yeah,
that's pretty cool to see it all in one chart.
Yeah, it is pretty cool. I use a dynamic selection to automatically just add all the layers to one chart. But if we go back to this chart, you can kind of see that there is this like increase at around 300,000 tokens, and it's only the green run. So which means it's the layer norm that was ablated that creates kind of like this massive increase, but it did then stabilize itself. But if you zoom in, you can see that all of the other ablation studies kind of were around, their gradient norms never went over something like 500. Although there was a particular layer from when we ablated dropout that layers 0 and 1 had a much bigger kind of impact, but then everything kind of did converge as we went. If you look at kind of like this global gradient norm, you can clearly see that there's this massive spike when you ablated the layer norm right in the beginning. But again, you zoom out and they kind of all have converged. So nothing really completely unstable. Nothing completely unstable, but there definitely was some interesting areas that happened.
Was that with gradient clipping on or completely off?
Yeah, with gradient clipping on. With gradient clipping off.
I see. That's one of the,
Yeah, with gradient clipping off, we didn't actually even have a result for this final output. So there wasn't anything actually created for that. Yeah, so if you want to then look at the activations and how that changed, I created a little section here to show all of the activation distributions per step of the model, so we can kind of see between all of the ablation studies how that performed, right? So if we go look at if we go look at what happened through all of these, we can kind of see that on every layer there's a very interesting kind of distribution pattern that happens, right? And if you look at kind of these middle layers, for the green graph, they kind of all have a very concentrated distribution around 100, or there's 100,000 counts of that around very small values of close to 0. But as the training then progressed, you can kind of see that green's distribution increased. And you can see that kind of through all of the different layers, which was pretty interesting. So you can kind of see at this high level how that distribution came out for the green.
Oh yeah, you can see the green widening on the multi-distribution chart.
And the green was particularly when we ablated the layer norm, which was pretty interesting. And the other interesting thing that you can kind of see from this like pattern that emerged is that in the beginning stages, when you ablate the layer norm, there's kind of like
double hump.
Yeah, this like double hump distribution, which I'm not actually sure why. It would be really cool if someone that watches this video could tell us.
Maybe someone who actually knows what
why,
indicates.
Like, so why ablating the layer norm would create this kind of double hump distribution, especially in the later layers of this particular model. But as you can see, as you progress through training, it does start converging to very similar distributions to the other ablation studies that I did. But you can still see that kind of double hump flat top pattern appears, and I'm sure it will start flattering out more and more as we progress. But you can also see that with longer training on the pink graph, there's also this double hump, and the pink graph is showing us that if we clipped our gradients, so if we ablated our gradient clipping, that kind of double hump pattern is also prevalent, and you can see that on the chart. Yes. It's also prevalent there, but the yellow one is if we ablated a dropout, but that has a pretty stable, there's no like very interesting distributions that happen across any of the patterns. It's pretty kind of normal distribution across the mean. if you look at the yellow one, the yellow chart as well, which is, again, when I said we ablated the dropout, it actually had the best convergence after 32 million tokens, had a pretty decent convergence. And even on our evals, it seems to be the one that performed the best. So maybe there is kind of some correlation between the dropout layer of GPT-2 that we don't need.
Yeah. So the perplexity is calculated on the eval?
Yeah, the
set?
perplexity is calculated on the eval set. And the eval set was just after every kind of 65 million tokens or so. Another question that came up was, did some changes improve convergence speed? And that's just literally what we're talking about now. So if you look at the training loss, ablating dropout clearly gave you a better convergence or a essentially better model. What we have to probably run some evals on that to confirm. But that seems to be the case in this particular experiment. And then, are any certain layers critical to stability? As we went through all of this, the model did produce results for all of them. They all did converge to some point. Maybe if you look at ablating the layer norm, maybe this would have flattened out a lot sooner and maybe kind of converged to some sort of local minimum. Maybe it would have diverged at some point if we kept training it. So to answer that question, from the studies that I did, are any layers critical? Not necessarily. Of course, there are certain layers that are critical to this, but not in any that have shown signs of very big instability. There wasn't kind of any massive gradient spikes happening. There was no vanishing gradients or anything like that. It all seemed pretty good. Maybe the activations, there could be some information that the audience could give to us, like on the earlier layers, very narrow distribution of the activations here, but nothing that shouts that it would cause massive instability.
Did it actually give you the answer that you need to pick the right, architecture for the next trainings?
Yeah. So it showed me that potentially maybe if we cut dropouts out, that paper or that kind of blog post that I read about it having better convergence, maybe we can do that. It's not something I did do because the difference wasn't that big, but it's something I definitely could do to help with the convergence speed of the model.
So you didn't want to take the risk, basically?
No, I didn't want to take the risk. We know GPT-2 is stable enough for that. But yeah, probably something I could do from this investigation.
Yeah, fair enough. And then when you showed me at the bottom, you have 4 nice experiments. But did you actually have to rerun them when you are working on this? I imagine it's the first study, so you do have to do a little bit of debugging.
Yeah, there were actually. So these are the main kind of experiments that I ran. But if I change to this runs tab, you can see that there were actually a lot of different repeated runs that I needed to do. You can see the ones that don't have metrics were potentially the ones that didn't have any values were the ones that failed. And then I added some descriptions on some if things didn't work or they did work. There was actually on this, if we go and run some of these, where I actually figured out that there was something wrong. So I had these experiments before, and if you look at the same report, you can see that there's quite very even distributions that were happening. But what was interesting is that there were these kind of gradient spikes that happened. And this kind of showed me why were these spikes happening. And it turns out that I was using a subsample of the data set, and it was just for testing. And then I was running it and I realized, but why are we hitting these massive spikes? Turns out if I changed the axes, I was actually running multiple epochs because the data set was too small. But with the language modeling, you're not really going on epochs, you're going on number of tokens. So it then helped me know that I needed to change this and see what was particularly going wrong. But of course, because I can visualize these spikes really quickly, I should have already known to stop it over here, but they weren't really massive ablation studies.
Cool. So how does it work when you log multiple runs? Because I see the experiments are, some of those runs use the same experiment name. When you log a new run, does that retry the experiment effectively?
Yeah, so it's effectively the experiment gets a new run ID, and you can have multiple runs that have the same experiment name, because the experiment name is the kind of the idea that you're following the longer training run, and it kind of helps you just make it a little bit neater, and you can then flip between experiments and runs.
Is this basically showing the latest run for a given experiment?
Yeah, it's showing the latest run that was tracked to. So it's actually its own unique value, it's its own unique run, but that experiment name is that main idea, and it helps you just neaten up your workspace. But if you change back to the runs, you can actually see those ones we highlighted are still there.
So Leah, I see you also did quite a bit of editing in the report to like have the custom x-axis in the chart and the multi-run, multi-metric chart that you showed me. So how difficult was that actually?
Yeah, so it was actually pretty easy. Neptune has quite a lot of functionality to allow you to create dashboards and charts and pull them into things like reports. But one thing that I can show you is this is a report that will stay persistent. I can quickly show you a way that helps answer one of these questions. So if you have a report and you want to add additional information to it, we can maybe answer the question on, did some of these changes improve convergence speed really quickly? So what you can do is you can just edit this report. You can then search for another metric, right? So I can maybe search for something like tokens, but I can see that I don't maybe have that particular metric in this report. But with Neptune, it will find if there have been any other metrics logged with that namespace. So what I can maybe see is I want to see the number of tokens seen by my model in terms of relative time to have a look at convergence speed. So what I can do is I can now add that to this particular report, right? I can then go and I can edit this, and maybe I can change the x-axis to relative time. I can save that, and what I can now see is to get to the same number of tokens, final of about 30 million, I can see that, again, we came with the same conclusion that if you ablate something like one of your layers, let's say in this case, the layer norm actually had a faster convergence speed to, say, the one where we ablated the layer dropout. So in this case, if we now publish this report, we can now see that particular result in relation to the better convergence. So what we then saw earlier, and the conclusion that we had come up with, was we're not really going to do anything because the difference in the final loss value was not that great. Although ablating particularly the layer norm had the kind of worst, let's say, final loss value. But in terms of the convergence speed, it actually did converge in 3 minutes faster. So there was kind of some higher throughput on that. We'll dig into the throughput when I go look at more of the hardware metrics. But this kind of just shows me that maybe we don't need to do anything. Let's just keep the model architecture of the GPT-2 pretty much the same, and we'll just carry on with the continued pre-training. But as you can see, this report is now published. We've even added another metric. It's not difficult to add stuff to these reports and create them out.
Yeah, and even if you don't have edit rights, you can still browse the other charts related to this report. You just cannot really save them, can you?
Exactly. So I am the report creator. This is the edit rights that I have. I can now share this with anyone really in the organization, copy link to this report, and they will see exactly what I'm seeing, the same colors, the same charts, the same selection. And you can even come refer to this a bit later. Awesome.
Should we continue to the hardware metrics that you mentioned?
So to set the scene on this, what I really want to do is I needed to be able to determine what kind of GPU. Would it be like an A100, H100? Maybe those are very like top grade GPUs. Maybe it'd just be a simple RTX 5000. It also depended on the price, but I wanted to see kind of what GPU I needed to use for the type of model I'm training. So the model size, does it fit into memory? What would be the throughput on that? And then essentially kind of how much that would potentially cost us for 1 billion tokens. So what I did for this is I did a kind of, you could maybe think about it like HPO, some hyperparameter optimization, but these are just kind of I changed things like the gradient accumulation steps. I changed things like the per device batch size. I changed the number of GPUs, the type of GPUs, and I ran them for not 1 billion tokens, but I do a calculation at the end that I'll show you of what this potentially would cost for 1 billion tokens. So the data set that I had for this model actually had 6 billion tokens. But in the longer training runs, I wanted to kind of see what I could do with 1 billion tokens. So that's kind of why I do the calculation in terms of 1 billion tokens. But that's kind of setting the scene. So again, I created a report on what this would look like. I ran a whole bunch of different experiments. So I did all this with DDP, so some distributed training and putting data parallel. So there probably is a little bit of losses and kind of model training optimizations that are gone into kind of sharing and moving that model around. So there's all of that, but essentially just on a high level, what did I need to train this model most effectively so I could do as many runs as possible and save money, right? Mm-hmm. So I did a couple of these. I did ones where I used 4 A100s that I ran through. I used ones where I used some A5000 Pro, so like an Ampere architecture, because I read that you could train Ampere architectures with BF16 precision rather than FP16, and apparently it would give you better performance. So I tried that out. I tried RTX 5000s, and I tried a whole bunch of different combinations. I also tried these different combinations out with the different number of GPUs, different number of context lengths, so how big of a number of tokens could fit into the model. So I trained it on a number of different per device batch sizes. So you can see I tried 18, 16, and so forth. I also tried it on different gradient accumulation steps, so 16, 32. I was getting ooms in and out of here, so I just kind of recorded that in maybe like a description. I archived all of those runs because I didn't really need them in the main comparison. I also looked at like the final number of input tokens seen at the end. I looked at, of course, what was the GPU name, and there was like maximum number of steps. I tried to run them for the same number of steps, but if I kind of saw convergence wasn't happening or it wasn't really performing better than something else, I kind of just killed it. Yeah, so that's kind of what I did, and now you can see these metrics, right? So again, main training details, the high level, we needed to look at the loss. Does any of the losses keep converging? And you can see that they do, right? So if I'm using something like the A5000 Pros or the A100s or even the RTXs, they are all converging pretty similarly because the seed was the same. The kind of some of the parameters were pretty similar, and you can kind of move through that. There were some that I kind of like canceled and cut off, probably could have maybe let them run a bit longer, but that wasn't really the main thing. I really wanted to see this throughput and determine what kind of hardware I'm going to use. Another big version that I use, and we kind of saw something similar in the ablation studies, was this idea of the number of input tokens seen to the relative time to kind of look at throughput, right? So what I could see here is that the two best performing configurations were definitely with the A100s, and the next best ones in terms of the number of input tokens that are being processed versus the relative times is the A5000 Pros, right? So we can clearly see that from this particular graph. So essentially to me, that meant everything else was good, but I should really focus on those two. If we look at like the training configs, so I got like training configs versus the number of tokens seen, we can see like if I'm using things like particular gradient accumulation steps, so like if I use like a 32 gradient accumulation step, how many average number of tokens seen does that produce? But if I use a 16 seemed to be like a good one, especially when it came to using those A100s and the A5000 Pros. Same here with like per device batch set size. So try to maximize the GPU. So try to use a big of a batch size per the device in combination with the gradient accumulation steps. We can see here that we have some pretty good results again when, well, not really, like with a bigger batch size, what you had to do is actually, with a bigger gradient accumulation size, we actually started using a smaller batch size. There's probably some nuances in there. Number of GPUs, of course, as the number of GPUs increases, naturally, you are going to produce more tokens, but then there is kind of like those interconnectedness between the GPUs of transferring the model and averaging it out and bringing it all to one rank, and then recopying the model across, that plays a factor. So you could kind of see that relationship. I also looked again at, the gradients accumulation steps, and just try to kind of like get an understanding of how this model was performing. To make sure that I'm actually maximizing the GPUs, what I was looking at is the memory utilization. This is particularly across the GPU, so you can go and see into each GPU what how much it was using. What was interesting is that generally on GPU 0, which was kind of rank 0, the main one, it always had a higher memory utilization. Of course, that's where most things were happening, so it would actually be the limiting factor of my distributed computing. So I always look to try maximize that. Although most of these runs are happening at around 60%, what I found is like if I started like trying to increase the batch size and things, it like just burns a lot more. So I kind of try to optimize it that way. And then if you want to look at the GPU percent over all of them, on all your GPUs, again, you can kind of have a look at that. So that was just to kind of get a feel for what this was like. But essentially what I could see from these final results is that the A100s and the A5000s were really probably doing the best. But what happened, what you'll then find is that they actually have a different price point on how much they charge you per hour. So yes, I could probably go with the A100s just based on the number of input tokens seen compared to the relative time, but I really needed to take that throughput and calculate how much it would cost me to process 1 billion tokens. So to do that, I could potentially use Neptune. I could go and log the throughput and then do like a multiplication using one of our custom expressions. But if I'm not also logging that and I want to do that in like a notebook and have it saved somewhere, I can do that with Neptune too. So what I did is, if we go to a coding part, is I used a notebook and our fetching library called Neptune Query, and I went and fetched all of my experiments that I used for distributed. So if I labeled any of my experiments by distributed, I fetched all of those. There weren't really a lot, but you could see like if you're doing like massive parameter sweeps, it could be a lot of data, but Neptune Query is really fast and performant. So to be able to run a couple of 100 experiments and fetch all of that information into Neptune is pretty quick. So we can see that that has come through. Then what I needed to do is I actually needed to fetch some of the other information. So I wanted to fetch things like the gradient accumulation steps, the number of GPUs, the token lengths, the per device batch size, and the GPU name. So I could like do some comparison analysis, very much similar to what we're doing in Neptune, but I can customize it a lot more.
Mm-hmm. So are these configs or are these metrics that you're fetching here?
So this that I'm fetching here using this attributes filter is actually just the config names. It's not the full config name because they're all being matched with regex. So got the gradient, accumulation steps, all this, or GPU num, all the max token length, etc. And you just basically fetch this data frame that then has all your information in it. And you can now go and merge and slice and dice the information as you want. This becomes also really important if you're doing like kind of massive hyperparameter sweeps and you want to get like visualizations across these different spaces, or you want to get like really big statistical measures across all of your experiments. Becomes really important to be able to do that pretty quickly. So this is just a really basic example of that. Then essentially fetch my metrics now. I can now fetch all of my metrics that contain train and tokens and my training loss, but I also have this flag to include absolute time. So then that will allow me to calculate the time taken to process a batch of tokens, and then I can do like some statistical measures by calculating the mean or the standard deviation on that. So that then returns me the run IDs that we had, those particular metrics like the training loss, the number of input tokens seen, and the tokens per second. And then I went and I used pandas to just process this. So I could calculate step duration stats, I can calculate the token diff, etc. So basically with that, I can then say per each of those runs or those experiments that I had, you can calculate the mean throughput or the standard deviation of that throughput. I can then plot it all on a plot yeah, probably could make my matplotlibs look a little bit more decent, but you kind of just want to get a sense of what your mean tokens per second throughput is, and you can then correlate that to a particular run ID. But the main thing that I really wanted to see here was how much that would cost me for 1 billion tokens. So if you have like a table that says a GPU type to the cost per hour, that's pretty easy to get on your providers, or maybe you have some internal metrics to understand that. You can then go and join that and merge it into a larger data frame, and now you can get your run, your mean throughput, the number of GPUs you do, the cost per hour of that, and how long it would take to process 1 billion tokens, because essentially you've got that mean throughput. So on average, to process 1 billion tokens for like an RTX A5000 would cost me about $14. Right, so from this now, I can now see that even though the A100s had a bigger throughput essentially, on average, it would be better for me to use the A5000s with the setup that I had to process 1 billion tokens on 4 GPUs. Yeah, so it would just be a little bit more cost effective. It means that on the longer term, while I was doing this, I could maybe have extra money to run more experiments, maybe more hyperparameters, and just really optimize my output. And that's exactly what I did. So I then said, well, if it's going to cost me this four GPUs, I can upscale it to 8, and I can do a few different longer training runs on 1 billion tokens. It's not going to break the bank for me to run this as a GPU per AI researcher, right? And that's exactly what I did. And the final result just showed that I could use a batch size of 8 with a gradient accumulation of 16, and so forth.
That's a really clever use of Jupyter Notebook, because what I see here is that you did go as far as you could almost.
Yeah.
In the reports, you said we could probably do custom expression here with some hard-coded values. Mm-hmm. But if you really have an external data source, you probably don't want to arbitrarily choose to do that in Neptune or in the other system, and then you can do it in the notebook anywhere you like, really, right?
Exactly what I did, and you could just get a nice quick summary, statistics, do some really fancy and customized stuff in your notebook. It does not take long to pull the data from Neptune, and it's 100% accurate on the data that you pull all the time. So those statistical values that you're calculating will just give you quicker insight. Of course, what you can now do is you can also log this back to Neptune if you wanted to. This plot that you've created here, you can add to your report as well, because the Markdown supports images. So you can then just have these references at a later point to ensure that this was the decision I made of what hyperparameters I'm going to use for these longer training runs, and refer back to it if needed.
That's a cool idea, actually, yeah.
Yeah, so that's what I did, and it actually worked out pretty great. Once I had this information, I didn't worry about out of memory issues anymore, because I kept running into those. Yeah. Sometimes I try to push the bounds a little bit and see like if I could increase my batch size and maybe see things that are happening. Something I did learn that was pretty cool is that with Torch, you should clear that CUDA cache sometimes. That also tripped me up, and Neptune helped me to find that, especially like on the utilization. I would run like an experiment again that had pretty similar setup, whereas it ran before and then I restarted the training, but then it went out of memory, and I was like, but why? And then would realize that it could see like there was like this increase in the utilization. So I needed to clear the cache. Actually, sometimes it didn't clear for whatever reason, but it was very, very interesting.
Yeah. So you use the similar hardware monitoring setup to what we showed earlier to get the CUDA utilization?
Yes, exactly. I used that same system metrics monitor script, that utility that we have. It was pretty easy to use, worked in the distributed environment setup. I just had to ensure that I was logging it from rank 0. Mm-hmm. Or initializing it.
You showed it actually does capture the metrics from every GPU.
Yeah, exactly.
Yeah.
So it will capture all of these GPU metrics, and then I just added them onto like a single plot. So now you can see in the legend, got GPU 0, GPU 1.
Maybe you can turn on the smoothing a little bit more aggressively, because it's a little bit hard to read that.
Yeah.
I think Yeah, there you go.
Now you can see all of those GPUs that we're using. So the ones I was really maxing out are at the top, or if we scroll through, we can see that I was really maxing out on the 4th GPU, this A100. So if we look at this particular experiment with the A100 or the 4 A100s, we can maybe now see like what was that batch size. So I could just maybe add onto the legend here something like config per device. Here it is, config per device train batch size. So now we can clearly see that if I pushed the per device by batch size up any more than this, I would have gotten out of a memory issue. So that's now telling me that my per device batch size needed to stay 8, especially on the A100s. If you go look at maybe like the A5000s, they were also pretty much maxed out with a batch size of 8, but they could have maybe changed on something like the gradient accumulation steps, right? So if I go gradient, yeah. So now you could clearly see that, let's go back to GPU 0 on the, where was this, A5000? Yeah, like on the A5000, yeah, there we go, A5000 Pro, we had like a gradient accumulation of 8, per device batch size of 16, but we weren't really maxing anything out just yet. But if you go kind of more over there, yeah, you could see that there was something I was actually trying to show. But yeah, then you could get like the relationship between what was my gradient batch size, what was my per device training batch size and my gradient accumulation steps, and whether or not you could push this to its limits. But we definitely saw that we're pushing the limits. Which one were we on that was showing the top ones here? Right? Oh, there we go, yeah. So on a 2 A100s, a gradient accumulation of 16 and a per device training batch size of 16 was pushing the limits.
Yeah,
so
it was like to perfection.
Yeah, so you can kind of see exactly what you need. So here is, I think, what the final config is that we went with. It was 4 A100 Pros with a gradient, a per device batch size of 8 and a gradient accumulation steps of 16. And then you could work out your kind of effective batch size from that.
Yeah, multiply. Yeah.
Cool. Yeah, so that's what I did. Helped me figure these things out. Was pretty neat. Yeah, and you could really like maximize and optimize what you're running.
That is pretty awesome. And I really like that you can use both reports and Jupyter to analyze those. So I think a lot of the customers that I talk with, especially some of the ones using other tools, they feel like locked in because those maybe have like flexible visualizations as well, but getting the data out is like slow and painful. Mm-hmm. And I think here you put a lot of data, like even some of the metrics for the entire run.
Yeah. Was very quick.
No downsampling, right? You just
no
everything.
No downsampling at all when you are pulling data using our fetching library.
Exactly. So this is what the researchers that I talk to often see value in. Not just getting the whole data out, but being able to quickly get it into a notebook, into pandas, to just wrangle a little bit with other data sources. Mm-hmm. Yeah, that's really great and a great example of that.
Yeah, and Krzysztof, you work a lot with these big AI labs, right? Do you see them logging and tracking these system metrics to Neptune, or are they using some other platform, and why
they do train off? Yeah, they do use both. So the common setup is most of them are running on Kubernetes or Slurm sometimes, but mostly Kubernetes. And so they do have an ops team that typically uses Grafana for something like just cluster health. And you could use that to filter down to specific job and see what your hardware utilization is and stuff like that. But many of the researchers actually prefer to see that in Neptune. So it often ends up being in both places.
Okay.
You could still see some of the teams maybe pulling data from Neptune and from Grafana to analyze that. But I think most of the users that I talk with, they prefer to see it in one report in Neptune. just because it's so quick and easy.
Yeah.
It's the tool of choice, right?
Yeah. I work a lot with kind of the startup teams.
Yeah.
And they love seeing the hardware metrics right alongside their training metrics. And it helps them to quickly correlate between, like, if they maybe see something that's gone wrong in your kind of loss, was that because of a down GPU or something like that. Yeah. But I'm sure on those bigger labs that you work with, they have hundreds of thousands of...
They have a lot, but they have the same kind of pressure to optimize their hardware. So what I see often is some of them even going as far as killing the jobs if they don't hit like a 60% GPU utilization mark. So yeah, you could do that with the Neptune query as well, right? That's you have the like API pulling the data, and then you control your cluster for Kubernetes to maybe stop some of the jobs and then to, make priority for the more optimized ones. Yeah, it does happen.
That's very cool.
But the startups do that as well. Like, I'm actually curious because startups are, in my experience, much more cost conscious.
They are much more cost conscious. They need to optimize their hardware, of course, because they don't have massive budgets. But at the same time, they're also pressurized to get results. So they really just track everything to Neptune, and then they will have a look. Maybe if they're hitting 80% utilization on GPUs, it's okay, especially maybe on some smaller runs, maybe during kind of like their hyperparameter sweeps, things like that. But definitely when they start going to longer runs, they try and max out the GPU, all of the cluster that they're using, so that they really are getting the most throughput, the biggest throughput for the smallest amount of money that they need, right? So that's really what they're doing.
Yeah.
But yeah, so now I did this kind of hardware analysis. I did the ablations. I got my choices on what to do for my longer training runs. I knew the parameters that I needed to set, and that's then when I decided to go in and upscale my model, put in the amount of money that I needed to on how long it would take to train 1 billion tokens, and I got some really interesting results, and I'd love to show you that.
Yeah, looking forward to see that. I think it's exciting. The monitoring of the long training is one of the reasons we rebuilt Neptune.
Yeah.
And so it is exciting to see how that will be used there.
Cool. Let me jump into it. Krzysztof, we spoke about my hardware analytics. We spoke about the ablation studies, and I kind of have decided to move on and train GPT-2, see if I can do some upscaling to it. I know the configuration of the GPUs I want to use, the number, the batch sizes, all those kind of interesting parameters to ensure that my training runs are running optimally. And I want to actually show you some of the results that I got from that, right? So what's on the screen at the moment is all of the different runs. To go and find these, I just created a quick little view to find them. So all of my pre-training jobs. And I had 4 main kind of experiments ideas that I was working towards, right? The first one was to take the base version of 124 million parameters with its original weight and just continue pre-training it for 1 billion tokens on this very high quality mathematical dataset. The second idea was to upscale and add 6 middle layers. So increase the model size to 167 million parameters. The third one was increase that even more. So start working towards the medium-sized GPT-2 model. So have the same number of layers, but maybe not the same width. So that gave me 210 million parameters. So these middle layers are also randomly initialized. So the idea is to get those layers to learn this new mathematical information while not losing any of the other knowledge that it has already acquired, right? And then the fourth one as another baseline was using the medium-sized GPT-2, also on its original weights, and continue pre-training with another billion tokens and seeing what that went onto. So this was kind of the main idea. When I was doing the upscaling, one thing I needed to make sure was that none of my newly initialized layers were failing or having exploding or vanishing gradients. I thought that monitoring those particularly, especially during kind of the first stages of training, just to see that they converge, would be good enough. So what I did is, if we go in here, I tracked again my general training information, so my losses, the perplexity, the gradient norm. But the main thing that I wanted to track here was the layer-wise activations to ensure that everything was training as it was supposed to. So what I did over here is I trained it for about 80 million tokens just to see that it was converging. So I did all my layer-wise logging. And as I could see from these particular layers, everything looked like it was training normally. So all of those new layers that I was adding, everything kind of looked like it was converging. So if we look maybe at like the MLP layer, you can see that everything pretty much converged. There's no kind of training spikes or vanishing, anything vanishing or kind of just erroring out anywhere. If we look at all of my LN1 layers, the activations of those, the same thing will apply. There was nothing really standing out to me, putting all these layers on a chart to kind of view that architecture. The same for the LN2 layers, everything looked pretty decent. What was interesting is that if I only plotted the activations for the middle only layers, so only those layers that I had added in, you could definitely see that there was something happening. So they're all randomly initialized at some point, and then they were definitely training, but there was nothing interesting happening that made me think that maybe the model isn't performing adequately. But you can see kind of like this like a changing of the model's activations as it's going through the training process. The same with the LN2. There was like some sort of initialization. They all jumped in the beginning, probably some warm-up steps that needed to be done. And then they kind of flattened out and converged. And the same can be applied, like if you just add a little bit of smoothing onto it, you can see that they were pretty stable. So it wasn't anything that I was too concerned about for this. And I primarily only did this for the 2 upscaled models. I didn't add in the model internal tracking, like the gradients and things, to the other versions, because they were essentially already stable. You just carried on training them.
So the middle activations, the ones that you added, you can see that some of them are actually activating more quickly, right? The yellow one.
Yeah.
Which one was that? I'm really curious which of the runs.
Yeah. So if we go and look at that, this is actually the 11th layer in the model. So it's primarily very close to the ones that we added. So it's a bit closer to the front. But the one that's not activating very well is the...
Yeah, but what I see really clearly here is that is that you said the front or the back layer of the model was the top one?
Yeah, it was the front. And then the one that's not activating very quickly is actually the last one.
So that's very interesting, because it sounds like the almost like the last layer is not doing much activation wise until the previous layers actually train and then actually like pick up some of those like features that will be learned later. Very interesting.
Exactly. And if you look at actually those same layers, you will be able to see them in this chart over here. So if you zoom into there, you can actually see that those are the middle layers, that kind of fanning out pattern that's learning. But you can see that all of the other layers are pretty much stable because they've already trained. There's not much more activation going on with them. They've already got some knowledge embedded. So you can kind of, what's nice is you split them out. You can kind of see that change that is happening.
And these are mean activations?
Yes, these are the mean activations. Of course, like you showed earlier, you can log any other statistical measures. Well, we probably could have also used histograms here, which might have been nice to kind of see the distribution. But in this case, I didn't do that. I thought it would just be okay on the statistical, on the kind of just the aggregated side. So yeah, that's what I did there.
Yeah, you see it's learning something for sure.
Yeah, exactly. Probably could have also looked at the gradients and had a look at those too. But for those, I didn't necessarily create some views. I was just going through and looking at them at a high level, making sure that if there's any spikes happening or any vanishing gradients. Nothing really stood out to me during training, so I wasn't too concerned by that, but it was there in case something went wrong in the aggregated loss. Then I could have come back and try to dig into that information more. So if I did want to go and see any of the gradients, then I could just come and look here and see if anything went wrong. Right, so let me go into the dashboard. But when I was running this, I was actually running it in dark mode, and it looked really, really nice. So I want to show it in that mode because I think you can see the visuals. Cool. So change it into dark mode. So we got the general training statistics as I mentioned. You can track all your layer activations. If you did want to add gradients, you could see those as well. I did the standard evals, so the text generation ones like Rogue and Blue, just to kind of see if the model is getting better or worse, how is it going. But then I went into a little bit more custom public benchmarks, so tracking things like your ARC score, your Huller swags, your winogrands, your trivia QAs, and you can kind of see how the model then performs over time from the different checkpoints. What I did do is I actually was saving these checkpoints to an S3 bucket, and then I was running the evals asynchronously from that, which was really nice because then I didn't have to worry about slowing down my training loop. But as you showed in the beginning, right?
I did do the same thing. It's always the right idea to separate these things and optimize the hardware.
Yeah. So for instance, on like Arc Easy, you can actually see that the model has this somewhat general trend upwards over time. On something like a Huller swag, it kind of stayed a little bit more flat. You go look at winogrand, there was like some change in the beginning, but then the model started like plateauing out. Interesting information about trivia QA. I also ran this on five shots, so to try improve the result. It's not really great, but you can kind of see that from this like shaded area on the chart. That is actually the standard error that I've been logging from the Eval. So I added in this custom standard error just to see, but this clearly shows you that maybe you need to kind of run this more, or the model isn't really performing that well on this particular benchmark, and there's a lot of error that's happening during its calculation.
Yeah, looking at the values, all of the scores, even I'm assuming the white and blue lines are some kind of references.
Yeah, so the blue horizontal lines are to reference GPT-2 of what its benchmarks were for this particular benchmark, or its results for this particular benchmark. And these white lines are other small language models that I found online that have some public information. So in this case, I was looking at, does my model start performing better or worse than something like a small LM from Hugging Face? And I just added in these references just to give me an idea of how is my model's training performing. And then you can kind of see whether or not you're improving to the baseline version of this model or to other competitors out there. So for instance, on the trivia QA, you can see that even with our standard error, we're not very close to what the small LMs.
Yeah, but they're all pretty bad or pretty good. But I'm assuming these are all like relatively bad scores.
Yeah, the state-of-the-art models at the moment are doing really well, but to kind of keep it within this less than 300 million parameter class, I needed to evaluate to something.
All I'm trying to say is that seems on par with the other.
Oh, yeah.
Even though there's like the standard deviation is not really close to the benchmark, it's still not that far off.
Of course. Then looking at something like OpenBook QA, we're pretty far off of other small models like LM1 and LM2. We've also got Common Sense QA, but all of these you can kind of see with their numbers. I also went and was doing something like GSM 8K, so that's kind of like a reasoning benchmark. And over here, I plotted num shots 0 and 5. So this was just to compare flexible extract and strict match, just to kind of see how those two different benchmarks within GSM 8K compare. What I did notice is that this kind of model that I'm training is doing better than the small models, but it is interesting to note that generally GPT-2 was not performing better than these. All of their benchmarks came out higher. So what I do think might be the problem is I should increase the data limit on my benchmarks. So when you're running these language modeling benchmarks, you can actually, one of the parameters to make it run faster is to limit how much data is being run. And I should increase that, but then you also have to run that on another GPU. So putting myself in the shoes just to get a feel for it, I limited the data just so it ran a bit faster. But most likely, if I increase that limit, you'll probably see much more accurate scores that will be produced, not necessarily like like these, but you get a feel for what that error is, and you can see that oftentimes that standard error, or at least the first standard deviation, is actually a lot further away from the reference line. So there's definitely a lot of error, and you can pretty much see that with most of these, that there's quite a big area overlap. So yeah, there's definitely a lot of work to be done. And then the last kind of benchmarks that I wanted to specifically focus on was the mathematical benchmarks. So if we look at MMLU has a couple of different mathematics benchmarks. So first one is elementary benchmarks, there's high school mathematics, and then there's college mathematics. So what I did here is I wanted to see if this data set that I was using to continue pre-training this model would improve either one of those benchmarks. And then on the right here was improve them all on an average. So this is actually just averaging all of those three and showing what its average would be, whether or not it goes up or down. But you can clearly see that on like elementary mathematics with a lot more tokens, it definitely goes up. It kind of stays pretty flat, if not decreases a little bit on high school mathematics, and then stays pretty consistent with quite a bit of deviation on college mathematics. But on average, it definitely decreases, which is interesting, right? Because you're doing continuous pre-training, so essentially it should learn a bit more mathematics, but that could be a thing where we actually go and investigate the data set. But that's looking just at the 210 million parameter model. What we should actually also be looking at is comparing all four of these and what each of them did. So if you look at things like the general training trend, so let's make this a bit bigger. So the general training trend, we can definitely, what we do notice is that the 355 million parameter base model actually performed the best in terms of loss, which makes sense because it's got a lot more parameters or layers that it can learn in. It's optimized for absorbing more knowledge. So it was actually doing quite a lot better. We can see that the two upscaled versions weren't doing too much better than the base 124, which was quite interesting. Like there wasn't, between the 210 and the base, so I didn't end up running them for that much longer because there wasn't really much improvement. You can see that the gradient norm stayed pretty consistent. Yeah, so you can see that the gradient norms actually stayed pretty consistent. On general, with the evals, now you can kind of see them all compared with one another. What was interesting is, again, with the ARC Easy, the 355 GPT-2 probably did the best. But we do see a really nice upward trend with the 210 version. And if I continued pre-training that for a bit longer, I think we could have gotten some interesting results there. But the main one was kind of the mathematics, so you can kind of see compared to all of them. So if we look at the MMLU mathematics now, we can see that the one that was performing the best in mathematics was actually the 124 million parameter original weights base model after 1 billion tokens. So the 210 went down after 200 million tokens. It was not performing well. The 355 million model also had this downward trend, but what was interesting is that the 124 had an increase on average on MMLU's different mathematical scores. So you can clearly see that when we split out the three different benchmarks as well. Yeah, so some interesting results there. I think it was really cool to see how this worked, and to be able to see like what happened. What I would like to do probably in future is continue the trading, maybe for like the full 6 billion tokens, especially on those upscaled versions. Maybe with a little bit more time, you could probably see some increase in that, because 1 billion tokens isn't really a lot. And even in kind of the 210's case, I killed it I stopped the training after some time just because it really wasn't getting better. So there wasn't really any point. But, with experience, you could kind of see that even on the 124, it had like this negative trend and then it went up. So potentially there could be something that happens there. And then, of course, like I mentioned, probably running the limit for the benchmarks higher to reduce that standard error and get a much more accurate benchmark score is the right thing to do. but to just get some initial results on how I was going, that limit was there. But what was really cool is like I was tracking 2,000 different metrics for these runs, and it was really not a problem. I could scroll through them, go navigate if something went wrong. For instance, when I was actually training the 355 million parameter model, I actually had a couple crashes. So if we go and look, so if we go to our runs, what you can do is you can go and see where the model, at what point it crashed, and use that forking feature you're talking about to actually see how the model got better, so, or where it went off. So
I think maybe if you go to the table, you can filter by model size or one of the other config attributes to get that.
oh yeah, you can also do this.
There we go.
Yeah, so I can filter on that. There we go. Cool. So with forking or these long training runs, sometimes what can happen is the cluster died, and I found that happen at least twice on only training 1 billion tokens, which is really annoying because I didn't want to have to lose all that lineage and history that I had. So because I have this cool ability to do this forking, what was really nice is you can see kind of we now have these separate runs, but on the main experiments, it was one continuous run. But what you can see here is that I was training, and at some point after like 350 million tokens, the training kind of died, or the cluster died, and I had to start at that last checkpoint. And that last checkpoint was at about 341 million tokens. And that's where I'd saved the checkpoint. So I could just restart the training from there. But then what is nice is that you kind of get this like little overlap between the parent run and the child run. So you can actually see whether or not the child run is learning at the same rate and is kind of has restarted to some extent correctly. So you can definitely see that there's this overlap with these points over here that the model has kind of resumed and it's learning correctly, and you can now let it go. And that happened twice. So it happened once over here, and then it happened once over here again, and we had a really nice way to restart. Yeah, sorry.
This is basically like rewinding a run, but you don't lose the previous run data because you're forking.
Exactly. So you don't lose the previous run data. You can still go in and do some analysis. It's essentially its own run, but you're also inheriting everything from the parent. What does also help here is sometimes you have training failures on, especially when you're doing distributed training, you can have a training failure on maybe like one cluster, but if you're logging from like different, logging metrics from all of those clusters, maybe one of them dies and your loss diverges, you will then actually be able to see that. In this case, I was only using one node, 8 GPUs. I was only logging from the main rank. So when the cluster was terminated, everything just kind of switched off. My Neptune logging stopped. The model last checkpoint was saved. So there weren't any training spikes. But then what does happen is if you have that and you've not just rewound, but you've still got that history, you can go back and see, well, what went wrong? Maybe it was a data split that was used, or a particular batch that might have been not within distribution or something like that. Or it was the cluster went off, but it was a node. So you can then go and filter through all of your node layer info, all of your hardware information, and see if maybe there was a drop in GPU at some point. And then at least it allows you to debug quicker. But in this case, I just kind of had to fork and restart. I could have also forked, restarted, and changed the hyperparameter. You would have then been able to see something cool like that. But I'm sure you're going to show us how that works.
Yeah, but what I like about this one example here is that you can clearly see that you're actually doing a true restart. Sometimes it's not so obvious, right? Because you have you have scheduler on your learning rate, a lot of other hyperparameters. Mm-hmm. So when you kick off that restart from a checkpoint, you kind of need to make sure that it's actually a true restart and it's not resetting your learning rate to like something big.
Exactly.
That could easily destroy your entire training.
Exactly.
So yeah, I think it's good to have that all the data in one chart sometimes.
Agreed. Yeah, and that's kind of what I did. And I saw essentially the result from this was that, you know, I didn't produce a state-of-the-art model, but what I did see is that potentially increasing, doing continued pre-training could improve the mathematical capability on a very smaller model because of the few number of data points. But if we look at like the papers that have been published, generally the number of tokens to the number of models should be about, to the model parameters should be about 20x. In this case, it's definitely not, which could be why the smaller model did see some improvement, but the larger models did not. And that continued pre-training should maybe continue going for a little bit, maybe push it to 2 billion, 3 billion tokens and see how it goes.
I think it would be worth testing that, but also maybe instead of continuous pre-training, there's also fine-tuning, right? Which is slightly different. You could do maybe a little bit of reinforcement learning to just fine-tune that on the math data set.
Yeah, that could work, right? So one of the things I did read up on as well is that doing a little bit of continued pre-training on a domain-specific data set and then fine-tuning it can actually result in better results, especially on some of those benchmarks. So it's definitely something I can try. I did start dabbling in the post-training side and doing some supervised fine-tuning, but I think we'll save that for another video to show people.
Yeah, definitely an extra experiment in the backlog, right?
Yeah, exactly.
A lot of researchers mention the importance of having many different benchmarks, so different data sets, different metrics, potentially different subset of the data that they're looking into, just to get a reliable sense of how the model is performing. And I'm curious, like now that you've done this, how many metrics you'd like to track, what data sets and so on? What's the scale of the evals that you'd really run in an ideal situation?
Yeah, so I was tracking about 400 public benchmark metrics. Of course, some of those are the aggregated metrics. So for instance, like the accuracy of MMOU, college mathematics, and then the one standard error that gets produced by the public benchmarks. Of course, there are a lot more benchmarks that are publicly available that you can go and track. The ones that I put up as a snapshot that I was mainly focused on were ones that I could find reference points for. So for like the small LM series, you can find what their scores were, so you can have some reference points. But there are a lot of other state-of-the-art models that are particularly looking at very specific benchmarks, like if it's reasoning or coding or mathematics or whatever that might be. But there are hundreds of different benchmarks that are publicly available, of academics that are producing new data sets that are releasing these benchmarks that people can compare all of the state-of-the-art models up against. However, these are very much public. Companies and AI labs have probably thousands of their own internal benchmarks on proprietary data sets that they've acquired somewhere, on particular evaluations that they are trying to figure out how a model is reacting or responding or following instructions or reasoning through problems. So that kind of post-training side, evals, is becoming so big at the moment. So me to only be tracking 400 really is a drop in the ocean of what you can do. The other thing that we're hearing teams that are doing language modeling is they're doing things like vibe checks. So they are not just tracking numerical metrics, they are also tracking text-based metrics. So they are looking at how the qualitative approach of how a model responds to a prompt, or how a model is following instruction or reasoning through problems. So they might be at different checkpoints running an eval, but the eval is explain to me how to maybe code a Python class that does X, Y, Z. And then the research is actually reading this and qualitatively looking at what this model is producing. They are probably also doing this multiple times to look at the non-deterministic nature of these models and seeing if there's any differences between the prompts and giving it some sort of score as well. And then there's things like using LLMs to do that and using LLM as a judge. And I suppose you're going to touch on something very similar on your side.
Yeah, that's why I was curious about it, because when I in my conversations with all of these researchers, it often came up the vibe checks. That you mean that's the process where you actually derive new benchmarks almost, right?
Yes. Yeah.
You start with the vibe check, you log some samples. I suppose that's where you might actually find it useful to log those samples at first to like see the qualitative data, and then move on to maybe defining a metric, or at least prompting an LLM to track that metric over time and to track it internally. Yeah.
Exactly.
So to recap, it sounds like, you know, in a real world situation, you would see like hundreds or thousands of different benchmarks being run in parallel to the training run.
Yeah.
Is that also how you run your evals?
Yes. Yeah, exactly. So in this case, I was actually saving my checkpoints to an S3 bucket. And then as they were being saved there, I was running my eval task list, right? Like which tasks I wanted to handle. So I ran them all asynchronously. They logged here. My training run just kept going, kept saving checkpoints. And then I could come in and see this all in near real time. And then, like I said, I would kill that run because it honestly wasn't doing much better, and there was no point in carrying on.
Yeah. But you wouldn't see that just from the val loss maybe, or perplexed.
No, you would not, right? Because essentially, if we looked at the validation loss, they were all converging, right? But you didn't see how it was responding to kind of like out of sample data sets. And that's exactly where the evaluations are coming in. I think you would have seen a while back, one of the OpenAI co-founders literally tweeted, evals is all you need. And honestly, it pretty much is true, right? You don't actually need to have a validation loss, because you could kind of just use that in your data set because of the scaling laws. Everyone wants to put as much data into these models as possible. But these as long as your evals are out of sample, you can kind of see, because when people are going to use these models, they're not going to give it, the same prompts as the data that you're training it on. They're going to be giving it very unique approaches. People speak differently. Different English spoken in different places of the world is different. And the way people would type a prompt might be different. So you need to actually see this on out of distribution data.
Exactly. And you need to see also the data in the context that the users will be using it. So whether it's from like cursor, maybe in code, or whether that's ChatGPT, and then you're doing chat, the instruction following, and these aspects of it are very important, and they aren't captured by the normal loss, right?
Exactly.
These are nuances you have to test separately. Yeah. So that's why I wanted really to like go deep on evals in my kind of like day of life of the researcher.
Yeah.
Do you want to look into that now?
Yeah, I would be really keen to see what you did, and you did on different domains. So we kind of see this. Be nice to see the similarities, but also the differences, right?
Yeah. There are lots of similarities. I think what you said about samples, you're gonna see it's exactly.
Let's jump
that. Here I want to show you the evals setup that I put together for my diffusion image generation model. So maybe to recap a little bit, the model is a class condition diffusion model. So it's generating handwritten digit images based on the class, so a digit that it gives, it's given as an input. So to test it, because it's a diffusion model and the loss is usually like fairly slowly but converging, I developed a couple of custom evals to check how the model is improving in like real world actual usage scenarios. Let's see how this works on like a real example maybe. I'll show you the diagrams first and how it looks in Neptune, and then we can look a little bit in the code just to have some more clarity. So what I'm logging here is you can see that I have my eval namespace completely separated from the training namespace. That is because I'm running eval as one kind of like parallel job to the training job. Because those are namespaced, I can guarantee that there's no overwriting of metrics going on. Of course, Neptune would prevent doing that, but I still want to log my data, right? So I want to make sure that these are nicely separated. And for evals, I still log my configs, my environment files, and so on. But the actual eval script, eval job, what's doing is it generating samples. So for each class, each digit, I have various samples. So I think in this case, I run it with 3 samples per class. And you can see those at each step of the training, right? So I can jump to the previous step, and see how like if I go all the way back, you can see that this started with a noise, and gradually the diffusion training creates something that looks more and more like a digit. So in the end, we're generating a pretty good zeros in this case.
Very good.
This is just a sample though, and then to actually analyze those, I don't want to look at the hundreds or thousands of samples every time, right? So I'm calculating a lot of metrics. So the metrics are calculated for 3 different evals, 3 different evaluation tests that I'm running, and I think now maybe a little bit better to look at the code. So I had this Gemini evaluator, which uses Gemini API because it has a very generous free tier, at least at the time of me writing this.
Sounds like we are researchers at a very early age startup.
Yeah, very, very GPU poor.
Yeah.
That is true for sure. But yeah, I think it's a valid use case. I think the having the kind of like LLM as a judge setup that we talked about earlier is very good with the public LLMs. I think in this case I was using Gemma, so it's the open source Google LLM, and it's good because it's cheap, it's fairly versatile, but it's also stable. So I can kind of like reliably compare the outputs during various runs in my training. And what the script does is we have 3 different evaluations. After we generate the sample, we give that sample and a prompt to the judge LLM, and we get the output that we parse into a score. So the first test is it a digit? So we literally ask it, can you see a digit on the attached image? And we include the image, of course. And then we parse the 0, 1 score depending on what the LLM says. Second eval is a correct digit. So we ask what digit is it to not introduce any bias to the LLM kind of answering the question. And we get the response back and we parse it into like digit from 0 to 9, and then we compare whether this is the one that we wanted or not, the one that was the original class before we generated the image. And the last one is a 1 to 5 score that asks the judge LLM to grade the handwriting quality from 1 to 5. So 1 meaning it's not a handwritten digit, 5 it means it's definitely a handwritten digit. And that's like another way to like almost like a grading rubric kind of style judging. So we run those evaluations and we get various scores. And what I'm capturing, and maybe that's easier to look in Neptune again, is we have those 3 evals, right? So correct digit, handwriting, and is digit. And we calculate scores first for each sample. And then we also have average, min, max for the entire class, so entire digit 0 class. And then we further aggregate those for the entire, like 10 classes and all the samples in those 10 classes, right? So that average is much more like, it captures much more information because it captures all the classes, but we can also look at the average for digit 9, and you can see that's actually like perfect at the end of the training. So that's pretty good. And so when you put it all together, it looks something like, this. I think I had a report here. So we have the average eval scores from all the samples in this case. I just didn't put the subset in the report. But you can also look at the samples, right? So we see our zeros, our ones, and we can navigate through the steps to see other steps. You can see that the 2 is a particularly tough one, right? Because this is like not really a good 2. I think this is like a mirrored 6 almost. So it's there's still some learning to be done. But you can see how looking at the samples is actually much more powerful than looking at the raw scores. Because you could look at the score for class 2. We can actually do that. Maybe let me go to this view. Average for digit 2, and then we could do average score for everything. We have a few metrics. We have for each metric we can look at the eval scores. So if we see maybe this run, you can see that for digit 2 it's jumping between like 0.7 and 1. We only have 3 samples for digit 2, so it's not that accurate. But yeah, for instance, the handwriting, it's not so good for for GZ2. It's hard to compare with different scales actually, but we could put them in one chart later maybe just to see how it compares.
In my case, when I was running the evals, my shaded region was showing the standard error, right? In your case, what is this shaded area showing?
Yeah, that's a great question. So if we go back to the report, which has the same shaded area, I can actually turn on one of the runs that run in the background. So this is the shaded area. You can see it from multiple colors, of course. So the shaded area is the completion percent of the evals process actually, because the metric here is the average across all the samples from all the classes. And we want to get feedback quickly then only after running the entire eval suite. So what we do in the code is we actually send what's called a preview metric. So this is a Neptune feature that allows you to log the value of the metric with a specific completion percent. So in this case, I can show you how it looks like in the code exactly. So here's where we, iterate over the generated images and then iterate over the free evals that we have in a config. And what we do is we log the metric, the binary metric for this particular digit and sample, but we also log the previous scores with a completion percent, which is basically the number of this sample divided by number of all samples, of course. And that way we get the updated average, mean, and max after every sample. So we don't need to wait. We can see data. Here's maybe 60-70% completed for these last few checkpoints. So those evals are still running in the background, but we can see the score with 60-70% confidence. Not exactly right, but with some confidence that's not 100%. We can see what the score would be based on the value. So I think that's useful because if you're training and your evals take a long time, you don't always need to run them perfectly in sync, right? But sometimes you want to get that quicker feedback, and here you get instant feedback. It doesn't really cost you any serious time to send that metric after it's calculated, but it does help you to see everything in one dashboard. So I think that's pretty useful.
You're logging this from an asynchronous process, right? Are there any kind of ordering or order guarantees when you're logging from an asynchronous process? How do you ensure that these all work out when there's some sort of latency difference between a training loop and an asynchronous loop? And
yeah, that's a great question. So you saw the two Python scripts, right? One is train, one is eval. So train one runs all the time pretty much. That's the bottleneck at least in my scenario. But as you said, they could be faster or slower. Evals, it allows you to specify the step and so step implying the checkpoint that you load to evaluate in a separate machine, separate GPU. In this case, actually CPU, because we're using the publicly hosted model. So yeah, that's how you free up the hardware to not stop the training for evals. You run this in parallel, and and so these are async. And the only there are really no constraints on the order other than for each metric, each attribute that I'm logging. Once I log the fully calculated value, so I can commit the value for a certain step, I cannot relog it, right? I have to. The step has to be monotonic for each metric. But even if the training is at step 1 million, I can rerun all my evals from scratch if I haven't run them before. And that's how I get these results backfilled, for instance, for maybe I had a run that I didn't have a certain eval implemented in the past. I want to recalculate it, but because it's a new eval, it's a new metric name because I have all my eval names in the metric names, so I can always rerun it and add it to an existing run. But yeah, I do have to for every eval, I do have to run it in order. So I'm not this. This is not gonna run the step step 9K before it finishes the step 8K, or it won't finish this one before it finishes the previous one, just to maintain data consistency. Another way to get around that, if you want to overwrite some data, Neptune really doesn't allow you to do that, and I think that's actually good because you never overwrite your data, right? But you can use forking again, and you would basically fork your training experiment and create a new experiment where you just relog the eval metrics and everything else would be inherited. So that's another situation. I know some labs that actually do this. And for me, I actually prefer this approach because, again, I'm maybe working with a simpler case. But forking is also helpful in some situations. Especially if you like have good tagging and grouping, and even if you have these different experiments, you can easily group them in a report and see all the metrics for the from eval and training experiment in one place. But the biggest one for me, the biggest convention that Neptune really allowed me to do is have everything aligned on one global step. A lot of the other trackers that I saw, they like if you log out of different processes, it's really hard to like align those steps, and unless you have a lot of conventions. I think Neptune is simplifying this by just giving you like one step argument to like logging the metrics, and that goes for samples as well. Because everything is aligned to one global training step, the eval metrics, the samples have the same step indexing. And I don't see any reason why you would not want that. Like it's so easy to just see, okay, at step 11,000, my ones and zeros were good, but twos are clearly not that good. And then I can add maybe, another metric. If I want to add a training metric, like loss, I can see my loss, and I can actually, if I go to editing, I can add it to the report as a new widget. Let me just add it quickly. Train loss. And the nice thing about it is, when I hover over any of these charts, I have the shared cursor, so I see the and shared zoom as well, right? So I see exactly when my loss goes from this to this, what are my eval scores doing, right? So it's very easy.
On the images, are the image widgets synced if you change depth?
That's a good question. So they aren't in this version, but they will be probably when you're watching this. So yeah, coming soon. But we are working on this very heavily, and I think it's a highly requested feature. So I have no doubts that it will happen the moment we release this video. Another thing that I had here that I wanted to show you was a report that compares the multiple runs, right? So similarly to you, I played a little bit with the error bands. So instead of using the standard deviation, because I was capturing the sample level metrics, I could actually do min and max over the samples, right? So what you see here, this like highlighted overlay, this kind of like shadow behind the chart that's colorful, you can see the value of the metric, but then you also see the min and max, which are actually kind of broad here. But maybe if you zoom into the beginning, you can actually kind of see that, okay, in the beginning, especially the scores are not that different, right? And I think at the end, they get slightly wider. That is where I probably should capture more of a standard deviation. But it also could indicate to me that now, because they are so different, what I should probably do is to go into that brown training run and start drilling into, okay, what are the scores for this particular digit, or like scores for any of the digits for that matter, and just do like a digit /d regex and maybe the average.
They're so quick to search through these charts. It's absolutely ridiculous.
And I could actually go a bit further, and I think we can copy this regex. I'm going to go back into my report, go to editing. Let me just create a new section. I call it debug, because this is kind of a debugging metric as far as I'm concerned. And instead of pasting it here and selecting this manually, I can actually do the dynamic selection, which I think is what you did, right?
Mm-hmm.
If I apply it, we now see chart as maybe a little bit too messy, but if I add a widget, I can turn off the preview metrics because we don't really need it here. I will also increase smoothing a little bit, and we still have a chart with a lot of data in it, but that's because we have the 4 runs, 4 experiments selected. If I select only one of those experiments, that should be a lot more readable, and we can see which digits are the lowest, right? Yeah, and there is quite a wide range, right? Because like some of those get all the way almost to 1 in the end, but some of them are actually decreasing as the model is learning. So again, something that might go into tuning the like how the loss is calculated and or like other parameters. Another thing that I wanted to show you is the custom expression that I did. So you mentioned you could calculate some of the stuff in Neptune. I actually did. So this metric is what I called correct digit by is digit. So we look at the fraction of we only look at the kind of out of the digits that are considered a digit by our evaluator LLM, what is the percentage of the correct ones. So we can see that for this particular experiment, we're actually getting to 90% correctness, except for the digits that are just not really digits at all. I think that's pretty good. And I think you can see how the metrics are improving as well. Compare that to train metrics and loss, there's hardly like improvements in there at this point, right? Like if we look at the final step, we don't have eval metrics for this bit, but if we look at the last few metrics, this is where I tweaked the hyperparameters a little bit, but the loss is very, very subtly improving. This is, 0.049 to 0.044. And the eval scores are getting, I think, noticeably better in that last period. So,
is there a way to calculate the difference between steps to see how well the model is performing, or like how good the loss is improving by each step?
Yeah, I think you'd have to do what you did and put this into a Jupyter notebook or something, or log previous value as a kind of next step previous metric. I think, both approaches are kind of valid. I think Jupyter one might be cleaner. Like if you're doing this sort of deep dive analysis where you calculate custom metrics, you do like rates of improvement and so on, I would actually go to Jupyter probably. I think Neptune, where the big value of the reports is for me, is how quickly you can put things together, and then how nicely it looks, especially when you have spiky data and you have those anomalies. It really like doesn't hide the data, and you can pick those up. So evals are really all you need. Like, and you said it in your case as well. I think the everything that we discussed today is pretty similar across both approaches.
Yeah, just kind of different metrics that you'd be logging for your evaluations and
exactly
in the way that you
approach different data sets. But in the end, you always want to see the samples. You always want to see eval metrics, training metrics, hardware metrics. Mm-hmm. I think the more granular, the better. So I think, I can really see how that's the whole like scalability of metric tracking is critical to production grade training. I couldn't imagine, doing this without some reliable tool that can actually just like ingest all the data that I throw at it.
Yeah. What I found is that, especially when I was setting it up and testing it out, that I started adding more and more things as the trainings went on, or as I was learning what else to log. And what was great is I didn't ever have a problem with adding more.
Yeah.
So to me that was great, but also the asynchronous logging, having that global step value is so important because it allowed me to run evals sometimes 2 days later. Maybe I forgot to run a couple evals, or I wanted to run evals on a refined data set or a bigger limit. It then allowed me to do that to the same run and then compare them across the values. The global step as well, as you showed here, it allows you to then change the axes to different metrics that you're logging. So for example, with mine, I didn't have any step values. All mine is number of tokens seen, but because I'd logged how many tokens were seen at every global step value too. So to change the axes across all of my different charts was really easy because there's that kind of extra dimension that Neptune is taking care of for you and not just auto incrementing.
Yeah, exactly. And it's like so simple actually, right? Because like all you need is a metric that you log at every step, and you can use that for the x-axis, but you also use that for error bands.
Yep.
I used it as well in my like min, max, and average plot line for evals. So it's very, very easy. And I think maybe the part that is almost taken for granted by two of us at this point is, we didn't really have to like tailor anything to log a certain way, right? Like we just logged the raw data almost, like the min, max, average, yes, may be pre-calculated, but the number of tokens, the step, the like all the metric values, and then you can use any of them in those charts as x-axis. You can use them as error bands. You really like don't have to worry about the joins, and with forking you don't have to worry about stitching those charts together. And it's so funny when like all the researchers coming from other tools that we talk to, right? They always complain how difficult it is to like put together a lineage chart of all their experiments in order. And
and when they explain it to us how they have had to stitch it together, or they have like multiple runs, then they click to add them all to a chart, but they're all different colors, and they don't want that because they're trying to compare multiple runs to each other and see this full lineage. Then they lose that. It's kind of like what I found, especially with the colors, maybe something really simple, and we hear it from customers as well, is they associate a particular experiment with a color after some time, especially after seeing a chart over and over and over again. So having that consistency is so important to them too. But then having one chart or one experiment idea that you're following be a rainbow, it doesn't help them because it just gets confusing. And that's not how academic research is following. It's following a color, following a particular style. So definitely can see the putting ourselves in their shoes is been quite valuable, right?
Yeah. And I totally get the usual thing we hear. Experiment tracker really is something that in an ideal scenario, you don't really think about it, right? It's out of your way. When you need it, you look into it. But you don't need to think about how you log the data, how you structure everything. I think in this case, obviously there's a little bit of thinking, but I think it was pretty minimal. And so like stuff like having the eval and train metrics separate, that's quite obvious.
Yep. The most difficult thing for me was deciding what do I call my metric names.
Yes.
That path that we have, it's like, how do I just structure that? But once you have that flow to know, okay, I want to have a path with train, a path with eval. In eval, I want these benchmarks, or I want it to be structured by the number limit, the num shots, and then the benchmark. Yes. That was probably the hardest point because you want to be able to compare all of those things. But even if they were split out of order with regex, it's so easy just to start to match and add in them.
In those charts, I think also some of those names get shortened. So if you match all the various digits, you get the shortened because this is where the placeholder goes in the regex, right? So you have digits equals whatever, but you see the entire metric name, and I think it's very very convenient because you like kind of like condense the part that is different, and you have that in the legend here, and it's clearly highlighted. Digit 1, 2, 3. Yes, there's always like naming conventions and so on, but as long as you capture like all the information in the metric name, I think that's really like the only convention that you really need to think about, right?
Yeah, exactly. And once that was done, it was just about logging dictionaries really at each step.
Yeah.
And the bigger the dictionary is, I didn't even see any difference.
Yeah, me
in the logging speed.
Either. I think that's a good point to wrap it up. Maybe. Thank you, Leo, for sharing all the demos.
Thank you as well. It was a really great experience to see how this is done in the wild, right?
Yeah, and to actually get into the shoes of researcher who has a lot of GPUs. Maybe we obviously had a tight budget, but
a tight budget, tight timeline. But so do our researchers that are releasing state-of-the-art models almost every month, right? So.
Yes, I think that it's a really, really tough job, but I think I understand it much better now, and the tool that's required much better thanks to this little, experiment.
Thanks for your time, and it was great chatting.
Yeah, always good to meet in person. Right?
Yeah, definitely.
And I hope you enjoyed it as well. Let us know in the comments where we messed up on our experiments.
And where we could have potentially improved.
Yes,
these projects are public, so if you do want to have a look at them, you're more than welcome to go and comment and show us where we can do better. And if you have any feedback on what you need for an experiment tracker, let us know.
Yeah, if you're not sick of doing code reviews in your day-to-day job, please give us another one. It's what we're trying to say.
100%.
All right. Cool. Thanks again. And it was a great time.
It was good. It was good.